parents and get an adult to supervise you on what you're doing. The topic that we've chosen, sort of chemistry from kitchen to the world, I hopefully am going to take you on a little bit of a journey today, looking in the kitchen, but also using the kitchen and its chemicals to understand some of the issues at a global scale. So again, I should stop talking about the introduction and we should actually go and start doing some chemistry. So for me in chemistry, there are a few kind of very important general principles, which if we can remember those and we understand those, they will help us in many areas of science, not just chemistry. And some of those aren't very well taught. Sometimes they're not taught at all, these general principles. You're just given the particular facts. So what do I mean when I say that? Now, if I have a paper clip, and I do, if I have a paper clip, if I was to get a match, if I was to get a match and strike the match, get that burning, do you think I will be able, the paper clip will get hot, we all know that, maybe I will burn my fingers in a moment, but is the paper clip starting to burn? Am I burning the paper clip? Can anyone see if the paper clip is burning?
No.
It doesn't seem to be burning. Why? Why isn't the paper clip burning? Why isn't the paper clip burning? It's an iron or steel paper clip. It's fairly soft steel. It conducts heat, yeah. So I was still holding it here. It was still getting plenty warm at the end, but maybe it was because it conducts heat. Any other reason that it wasn't burning?
High melting point.
Sure, but does it have to melt to burn? A match doesn't melt to burn. Wood doesn't melt and it burns. So it certainly does have a high melting point, but why doesn't it burn before then? It's not inflammable. We don't tend to think of steel, iron, as being flammable. But we're going to move over to my other bench and we're going to look at some other bits of steel. All right, so we'll just head over there. Come with me for a moment. I think that's the one. We'll use this camera. And what I have here, we'll get those out of the way for the moment. All of those objects there are made from steel. Made from steel. The paperclip is made from steel. This is some material which we would call steel wool. We use it sort of in the workshop for cleaning things. So it's just very, very finely drawn out, spun steel. Chemically, it's identical to this. This is a slightly coarse steel wool. So it's kind of like a steel cotton. This is very, very fine. This is very fine. What I'm going to do is take a bowl. So this is a ceramic bowl. So it will stand a lot of heat. And first, I'm going to put the coarse steel wool into the bowl. And I could do a number of things, I guess, to try and get that to burn. One of the things which I think I'll do this evening is I'm going to use some electricity. So I'm going to use a battery. This, if you want to do it at home with your parents or in a school, you can do this just with a 9-volt battery. It doesn't have to be a very big one, but I use a rechargeable battery. And what I'm going to do is run some electricity through the steel object. Now, we've already discussed earlier that steel is a conductor of heat. It's also a conductor of electricity. So this is a 12-volt battery. It's got plenty of current. And I'm going to run some electricity through the steel wool. All right, let's see what we see. I might even just for the moment turn the lights down. My camera will probably struggle. Let me just turn off an extra light. I think you'll see that it's glowing. It's not quite bursting into flames, but it is starting to glow. And bits of it are burning. So it's not burning quickly. Rods that I'm holding, these wire rods I'm holding, they're getting very warm. A lot of electrical current is going through. The resistance is leading to heat. The heat is leading to it burning. If I blow on it, seems to go out. What I'll do now, so that was the medium coarse steel wool. What I'll do now, I just have to be careful that I don't accidentally set everything in the room on fire. I'm just going to take a little bit of the very, very fine steel wool. All right. If this is like your hair, this is like the finest fluff of a baby duck. All right, very, very fine, but it's still iron. It's still steel. Chemically, it's exactly the same. Let's see what happens. Let's turn the light down now a little. Let's see what happens. Now I'm blowing on it, and it looks just like a piece of coal. And it's not got electricity anymore. So just now, just with my breath alone, I'm able to get that steel to burn. So that was actually burning. And just using my breath, once I got it started, it was burning and burning. And we've pretty much burnt most of it away. If I wanted to, I could turn that over, burn the other side. I could burn all of it. Now that might look as if it really hasn't burnt. It's just been hot. It still might look the same. If I was to take a magnet now and try and pick that up, I would find most of it would not be attracted to the magnet because it's no longer iron. It's iron oxide. I've actually burnt it. So it's converted from iron to iron oxide. Any questions about that? So that never really melted as such. It got hot enough to actually burn. So that was burning. Let me just change cameras back. So what was the difference? They're all chemically the same. They all had about the same weight of iron. The weight of the paper clip was probably less than the weight of the steel wool and the fine steel wool. But the finer it was, the easier it seemed to burn. What do you think is going on with that?
The resistance?
The resistance? Even once it was starting to burn, I could remove the electricity and just blowing on it, it kept burning. So I could have done the same with a match to get that fine steel wool to start burning. And once it started, I could keep it burning just by blowing on it. So the resistance might have been what helped me get it started. So some people are going, well, there's burning takes, for something to burn, what do we need? What do we need for something to burn?
As there is oxygen between the iron atoms and oxygen is needed.
Sure. So we need oxygen and iron. With my paperclip, what's the difference though? What's the difference? This is iron, and I got it hot. And the steel wool I got hot, and there's plenty of oxygen around here, and I was blowing on both of them. This didn't start burning by itself. The steel wool and the fine steel wool did. One of the things which is really important in chemistry, in science and biology, but also chemistry, is something which we call the surface area to volume ratio. So it's how much surface area something has for how much material is inside it. So a sphere has got a small surface area, given how much is inside it. A flat sheet of paper has got a lot of surface area, only a small volume inside. And when things need to burn for chemical reactions, those reactants, the oxygen and the iron, need to come in contact with each other. And if you're like a big spread out sheet of paper, you've got a lot of surface area. And that means the oxygen and the iron can react with each other over a large area. And that burning creates more heat. That's what burning is. That chemical reaction creates heat. And that heat speeds up the reaction, so more burning happens. And so when you've got something like this, even if I got it really hot, there would not be a lot of surface here for the oxygen to react with the iron to make enough heat to keep burning the iron. If I take something like fine steel wool, even though it's the size of an egg, there's oxygen can get around every side of every fine fiber. And so if it gets warm enough and starts burning, then a lot of oxygen can get in to make a lot of heat to make even more of it burn. So that's why some things will explode. So if you get flour dust, I'm sure it happens in India, it happens in many rural communities where you store flour. The dust, the fine dust, can actually ignite and create an explosion because there's a lot of surface area around those grains, which the grains can burn, but a large surface area, and that allows the oxygen to get to the iron or the flour or whatever is combustible, and so it can burn very quickly. So there's this idea of surface area and volume. It's important in lots of chemical processes, particularly these days. Let's have a look at something which is probably more familiar with you, although some of you might have done that experiment before. Let's go and have a look at another activity. I do like doing chemistry, but it does make a mess. It always takes an extra day to clean up in here. I'm sure in your science classes, you will have already, or perhaps soon, you will have started talking about acids and bases.
Yes, sir.
The concept in chemistry, we often use a scale to kind of describe how acidic and how basic things are.
pH scale.
Excuse me, sir.
pH scale.
Yeah.
Sir,
Yes.
I did the neutralization reaction once.
Excellent. Excellent. We may do some neutralizations today. Did you do that reaction at school or at home?
It's at home.
Okay, great. What I have here is some indicator paper that you can use to tell you whether something is acidic or something is alkaline. This pH paper, this indicator paper, you can make yourself. And you can probably tell from the color, but this indicator paper is just made from turmeric.
Turmeric.
Yep. So when I make my indicator papers, I'll get some ground turmeric. I will mix the turmeric up with some water. I'll also, if I can, if I've got some alcohol, so methylated spirits, some alcohol. You might use hand washing liquid these days, some alcoholic hand washing liquid if you are allowed to get that. And I will mix that in, shake that up, and then just leave it settle. The alcohol in there helps pull the color out of the ground turmeric. And once it's settled, you can pour the liquid off and you're left with this wonderfully brightly colored yellow turmeric extract. And because there's a bit of alcohol in there, I can just take that out, brush it onto the paper, the alcohol evaporates, and now I've made some very strong, strongly indicating pH paper. So this is just made from turmeric.
So it's garnet and red in base.
It does. So this is what we can use now to test various ingredients around your kitchen and to see which ones might be acidic and which ones might be basic. This is just some water.
It's neutral.
So it's neutral.
Then no change is gonna happen.
How do you know that it's neutral?
Because it has a pH of 7 and it shows no change when we dip in a turmeric.
So that's a lot of guessing. That's a lot of guessing. Absolutely pure water is a pH 7.
Water.
Most of our water that we get to drink isn't
It shows no
7.
change in acid.
Slightly acidic, I guess.
Well, it depends where you are. In some parts of the world, they have limestone mountains, and the water goes through the limestone. And it's very alkaline. Other parts of the world, it's different. So if I put the paper in here, what does that tell me?
No change.
There's no change.
No change.
So what does it tell me?
It tells me that it's either acidic or neutral. Any of
Okay. It just tells me that it's
not basic.
It's probably not basic, because let's just try and we'll just see what the turmeric extract can do. Just put a little bit of the turmeric extract in those. I will add.
Sir, what is this liquid?
So this is just water, and I've just added some of the turmeric extract into it. So I've got some vinegar here. I'll put some vinegar in.
Acetic acid.
Let's make it
acid.
acidic.
Yellow color.
Acidic, and maybe it's gone a little brighter yellow than before. Maybe a little. Here, I'm going to put a little bit of ammonium hydroxide, just cloudy ammonia. We would use that in sort of in cleaning.
Red.
So red.
Yes, sir. Red.
Red.
And kind of deep red. If there's any group of school children on the planet that should know what happens with turmeric, it would have to be you guys. And if we get something which is kind of somewhere in between, I've got a solution of sodium bicarbonate. So just a concentrate. So it's baking soda. So what do you think might that be?
It's basic. It's basic.
Red color.
It's basic. Not a strong base, but
so we can see
base, so it's not dark.
It's moved.
Dark red.
So it's alkaline.
Orange.
It's basic. It's moved the color a little. Now, turmeric is great. It has this good color change, but to get dark red, you really need very alkaline materials. So it's good if you're testing those. You can see that it has made a change with the bicarb. But one of the things which I also like to use is to go and get other plant extracts. So this material here I've just made from a blue pea flower. They do grow in India. They're more common in Southeast Asia. But if you can find any flowers, particularly blue flowers, some red flowers, but not many yellow flowers, if you grind the flowers up with a little bit of hot water and a little bit of alcohol to extract the color,
So China rose?
you can go and get a different indicator. Not every flower will do it. Red beetroots will do it. This is actually extracted, sorry, this one is extracted from a red cabbage. This one's extracted from a red cabbage. And so if I put this again into our water, here in Canberra, the water is pretty close to neutral. And if I put, again, some vinegar in here.
So pink.
Made it acidic.
So acidic. See what the color change is. I'll put a little bit of bicarb
Green.
in here.
Yes, we got it green. Not
well,
green.
Green.
It's sort of a blue.
Yes, blue-green
Depends.
actually.
And in the very alkaline ammonia, dark
There's
green.
It's a green.
Yeah, and so I
Like a
encourage you.
watercolor palette.
Yeah, we've got a very nice collection of colors, but we could actually use these now to not only just go and test things. For example, I think one of the students said they were doing neutralization reactions. Well, you could actually use that to test how concentrated your vinegar is. Vinegar in many parts of the world gets watered down, adulterated. So the people selling it would like to make more money, so they mix water with their vinegar. And I find that sometimes I'll get to a country and I'll buy some vinegar for some experiments, and it really is very weak because it's been watered down. But you could test that. So you could compare, set up a standard experiment, and then test how many drops of different vinegars are required to neutralize or get the color to come back. And so even if you don't have sophisticated scientific equipment, you can still, just with a straw and some drops, test and actually see whether or not some of the vinegar you're getting has been watered down, or which ones are the strongest vinegars. And so you can do good science literally with the material you have in your kitchen. You can be more precise if you've got scientific equipment, but the science is still as good. It's just the numbers aren't as precise if you do it that way. So let's have a look at, we've got pH indicators. Many of you have been studying pH at school. Rather than just using that to go, oh, this is acidic, this is basic, let's actually use the indicators to look at something else, to actually help us think about and study something of quite global significance. Now, just to set that up, I will just change camera. So now just kind of looking horizontally for those of you that might be getting a bit disoriented with all the camera changes. And I'm just going to get a small bottle. Yep, that's in shot. A small bottle. I'm just going to add just some of my plain water that is probably very close to neutral. And because I like the red cabbage, and it does go off if you don't use it, so I'm going to put some of that in. All right. Let's make sure it's got a nice strong color. That's showing up quite nicely. And one of the things we should always do, I'm going to do something with this vessel in a moment. We should always have some controls so we can compare what we're seeing now to what we've seen before, just so we can actually tell what the change has really been like. So I might just put a little bit of this in here first. That looks all right. Now I'm going to make this slightly alkaline. And I'm just going to put in just the smallest number of drops that I can of the ammonia to go and get it to change color. That's pretty good. We'll just get it into through the blue and kind of into the green. There we go. That's pretty nice.
It then changes into green.
Yep, that's good. So that's where it started. That's where it ended up. This is what we have. This is what we have now. What I'm going to do now is I've just got a long plastic straw. I'm going to put the straw into the bottle and I'm going to start blowing through the bottle.
Sir, it forms carbonic acid.
The carbon dioxide is causing it to change,
The carbonic acid.
making it acidic.
It makes acidic.
Okay, so hasn't quite got back
Sir,
to the original.
because it
Yes,
forms carbonic acid.
Forms carbonic acid.
Yes,
That's why it changes
How do we?
color.
How do we? Let's before we start answering that. What did we see? Let's focus on our observations. What did we see?
From green, it changed back into red, but not totally red.
Yeah, so it changed back. What else did we see?
We see that as it was not purely carbon dioxide, so as it had some other mixed gases in it, so it didn't change it totally back. It's kind
So
of green now.
did anyone see carbon dioxide?
No.
Can't see it, guys.
No one saw carbon dioxide. You're applying what you have heard before. All right. One of the other things which is an important thing which you haven't observed or haven't heard you say, this hasn't changed. So this changed when I was blowing through it. This started off the same as this. I didn't blow through that. This hasn't changed. That's important because maybe this was just going to change back anyway. So we did a control to make sure that this wasn't just going to change back just because of time. All right. So often, once you know a bit about science, you're very keen to apply it and leap forward to a conclusion. And then everything that you see, you use that to confirm your hypothesis, confirm your guess. And that's actually not good science. It's kind of the opposite of good science. What you really should be doing is observe the changes, certainly take what you know, but you should be trying to disprove your hypothesis. So because you've heard about carbon dioxide in your breath and carbon dioxide dissolving in water, making it acidic, that's what you've assumed is happening here. And it might be. That might be what's happening. But the question that I'd really ask you is, how can we test that? So you're telling me about carbon dioxide dissolving, making carbonic acid, and that we're seeing the change. And that would explain, if that happened, that would explain what we've seen. But I've got another hypothesis, and that is that me blowing through here, the gas just took the ammonia and brought the ammonia out of solution. So me blowing through there wasn't the CO2, it was the bubbles taking the ammonia with it out of the liquid, and that's why it went back. So how could we test your hypothesis and my hypothesis? How can we test those ideas? Because that's the real part of science. That's the real part of science. How do we test that? It's all very well remembering that you've been told that your breath has got CO2 and that it'll dissolve in water. And that's probably true. I'm not saying that's not true. But how do we test it? Because that's what science is about. How can we test that? You're saying it's the CO2 in my breath. I'm saying maybe it's just the gas bubbling through, taking the ammonia out. How can we do a test that can discriminate, that shows the difference between those two hypotheses?
So, sir, we can use an indicator.
Yes, but we've already got an indicator in there. We've already we've done this test, so we've checked that the indicator is showing us that things are acidic. We've got the indicator here. It's made the color changes.
We can use a pH scale.
Yeah, but that doesn't tell the difference between our two hypotheses. I believe, like you, that this is alkaline and this is acidic, and as I blew through here, it came back to be less alkaline or more acidic. I believe that, like you've been suggesting. It's just you're suggesting that it's because CO2 is dissolving in there, and I'm saying I have another idea, that the bubbles are just taking the ammonia away, which is why it's becoming less alkaline. How can we test those two ideas? How do we test it? What's a test that we could do? There's actually some very simple tests that we can do.
Maybe we can blow something else instead of CO2. I don't know, like using a pump or something.
That's what we could do. That's what we could do. So I could get a bike pump. I could get a bike pump and I could get a bike pump and just push the air through from the bike pump into there and see whether that changed the color. And what do you think would be the difference between me blowing and me using a bike pump to blow through there? What would you expect to happen if I used a bike pump? What do you think would happen?
So there won't be the same amount of carbon dioxide that was there previously.
Yep. So, but there'd be the same amount of gas. So what would you expect?
The proportion of CO2 to the other gases will be less.
Sure. Yep. There's more CO2 in my breath. Even though we haven't tested that yet, I'm prepared to accept that tonight. So what would you expect to be the difference between my breath and using a bike pump? What would we observe?
There's more CO2 in your breath and there's less.
We can't observe the CO2. That's not what we're seeing. What would we observe? So if I said,
as there is less carbon dioxide, then this process is going to be slower, and it's going to.
So focus on what you would observe. You're most of the way there.
We can observe change of colors in the indicator or something.
Yeah.
And feel the smell.
So if we set up two bottles the same, and I blew through one, and I pumped air from a bike pump through the other, if the CO2 is the important difference, if CO2 is the important agent, then we would see this change quickly. The one from the bike pump might not change, or it might change more slowly. There's still some CO2 in the air. So And if we wanted to do a better experiment, we could set up what we call a trap, just with some sodium hydroxide, caustic soda, and we could blow gas through there. That would take out CO2, that would trap CO2, and then the gas going in there would have no CO2. And we could see what would happen there. And so that's, to me, an example of the difference between remembering or understanding, or remembering facts about science, such as, oh, there is CO2 in your breath and CO2 dissolves in water. That's kind of a fact. Those are facts. It happens. And that's one part of science, but the important part of science is how to actually use your knowledge to go and make new discoveries, prove things, disprove things. And that's something which I encourage you to actually take the time to think about. So be a skeptic. So that is, if someone says, oh, there's more CO2 in your breath, I would always be asking politely, particularly if it's a teacher, how can we tell that there's CO2 in our breath? So you've told me tonight there is, and I believe there is, but how can we test? How can we test that? How do you prove that? How do you learn? How do you make those discoveries? So I think those are some of the things which are important.
And many teachers might get annoyed.
Sorry?
I said that many teachers might get annoyed by this.
Sure. So be careful about asking your teachers that, but that doesn't mean that you can't ask yourself that question and go and spend time to work out how you would prove it. Okay? The teacher, don't always go to the teacher for answers. You don't need the answer. You need time to work through how you would make those discoveries. So you don't need that answer. That answer isn't going to be on the exam. But if you want to become a good scientist, if you want to become an engineer that can solve problems, you've got to start solving problems, not just remembering how people tell you to do things, because that's a relatively modest set of skills, being able to remember things. And these days with a mobile phone, it's even less valuable. So to get a good job, you need to be someone that can solve problems that you can't find the answer on Google. Because if I can find the answer on Google, I don't need to employ you at all. So I need people who can solve problems I can't find the answers to. And this is kind of the difference between, I guess, how I'm working with you during these workshops and perhaps how your teachers work with you. They want you to get a good grade for your exam. I'm hoping to encourage you to be curious and keep working out how you can learn things. It is CO2. If we spent the time to do those tests, we would discover it is the CO2 in our breath that was making the difference. And we know now how we might be able to prove that, or at least prove there's something in my breath that changes it. So CO2 dissolving in the water makes it acidic. Is that kind of interesting, or is that a problem? Is that interesting, or is it a problem?
Sir, interesting.
Yeah.
Interesting.
I think it's both, because one of the problems that we have is that our planet is making more and more CO2, and we're putting it into the atmosphere, and that's leading to global warming, which is one large problem. But the CO2 is also dissolving into the water. It's dissolving into the oceans. In particular, dissolves into the lakes and the rivers as well, but it dissolves into the oceans. And as the CO2 dissolves into the oceans become more acidic. And there are many animals that live in the oceans. This is an egg from one of my chickens. It doesn't live in the ocean, but it has a shell like the shells on clams, like the shells on many of the small crustaceans that are part of the food chain that feed the larger fish that we eat. And all of those animals need to be able to make their shells. And as the water becomes more acidic, that water starts to dissolve their shells. and so they are less able to live. And so there are many big worries that we have across the world because of the acidification of the oceans that we've just seen an example of here. And so just imagine what would happen. You can do the experiment. We won't do it tonight, but imagine what would happen if you went and took an egg and put it into some vinegar and left it there. I think some of you may have already done that experiment. You will see the eggshell dissolve, and what you get left with then is, you know, an egg kind of without a shell. Now, whilst that looks kind of fun and interesting, that's not going to give rise to a chicken. And so that's the same threat to the life that we have in the oceans that's coming from the acidification. So while we're talking about the oceans, and I never seem to get through quite as much as I would like with this. While we're talking about the oceans, I'm going to set up another activity, one that you can try for yourselves at home. It will only take a moment. So easy to get the wrong camera. There we go. All right. Let's look at some liquids, some things happening in liquids. I've got here some large sort of glass jars, carafes, and into one of those, I'm going to pour some hot water. Hopefully not so hot that it cracks the glass. All right, so that's nice and hot. Probably 50, 60, 70 degrees, very, very hot.
That means we should use warm water.
If you're doing it, yes, use hot water from the tap. Don't use boiling water. So always be safe. So this is hot water. This is just room temperature water. And I've got one that I've just taken out of the refrigerator, and it's been sitting on ice for a little while. And so that one's cold. All right. And what I'm going to do now is just going to put a drop of food coloring into each one of those, and we'll just see what happens. So what are we seeing?
Dissolves the fastest in the warm water, and slightly slower in the room temperature water, and the slowest in the cold water.
Slowest in
Because
cold
in the
water.
cold water the particles are kind of densely packed, so they can't dissolve quite quickly. And if you're talking about the hot water, it's kind of the particles are have more space between them, so it can dissolve quickly.
So again, you're very quick to start trying to explain what you're seeing. I'm always keen to try and get you just to stop and actually look very closely at what's going on. Because if you think you know the right answer, you're going to stop looking. And sometimes that means you miss the real thing. And so what do we see happening? Don't try and explain what you think is happening. Just explain what you're seeing. It's very simple to look. We just have to do it. I'll just clean the condensed. So it doesn't, to me, look like it's just a difference in the speed. To me, it looks as if there are actually different things going on. And the food dye I put in was already dissolved, so it wasn't dissolving.
The food dye is already dissolved.
Yeah, so it's already in a liquid, so it just has to mix. So it's not like a crystal I put in, but it is a different liquid. We saw in the hot water.
First
Yep.
can is dissolved. First can is dissolved. Second and third can is not dissolved.
Sorry, say that again. Your audio is very quiet.
Sir, I'm telling that the first can is the food color is dissolved. Okay. Sir, second and third can is not dissolved. The food color.
So let's just have a look. Let's just have a look what we see. Do you see the food coloring moving here very much now at all?
Yes, sir. Yeah.
Do you?
Happening, but it's kind
Yes,
of
it's happening, sir. It's slowly is happening.
You must have very good eyes. If it's moving very slowly.
Yes.
Whereas, what about here? Moving.
a little bit faster.
And here it was moving.
It's already
very,
done.
very quickly.
2x faster is dissolved.
So what's actually happening here? We're going to come
So
back.
its kinetic energy of the particles is more in the warm water.
Well, that's true. But why does that mean we see this difference? So it's true, the warmer water, the higher temperature, the particles of the water are moving with more speed. How does that explain what we see? This is an activity that I could have done tomorrow night, but I thought I'll do it tonight. We're going to stop for a moment on this. Just going to move those very carefully to the side. And I'm just going to set up another activity, because we don't have to wait for you to finish thinking about one thing to start thinking about another. Here are some tanks.
Okay.
Here are some thin tanks. Into one of these tanks, I'm just going to put some normal water, just some fresh water.
Okay.
And into one of the tanks, I appear to have got a bug in there. I'll need to go and get that out in a moment. And so into one of the tanks, I've put salt water. Into the other tank, I've put fresh water. And I will just save
some insect inside.
Save a moth from there. That time of year. And just to make sure that everything is as similar as we can, top that one up. Okay, so one of the tanks has got salt water, one of the tanks has got fresh water. And I'm just going to put some blocks of ice into the tanks. I'd like you to think about which ones will, in which tank will the ice melt the fastest? Which will it melt the slowest? Or will they melt the same? The water is all at the same temperature.
I
The
think
ice
it
is
will
all,
melt faster in the salt water.
so I'll put the same number of ice cubes in each. So the water has started at the same temperature, the ice has started
Sir,
at the same.
the ice cube will melt in salt water very fastly.
Okay,
Yes, sir.
that's one prediction.
Yeah.
Let's see
Sir,
what happens.
it may melt in the fresh water fast.
So in the chat window, put down what your guess is, what your hypothesis is, your expectation. Just type in there whether you think it's salt fast or freshwater fast.
The salt water is the fastest melt. I think.
So I think fresh water.
Right? Freshwater fast. It's nice to have different ideas because
I think it is fresh water.
okay. I have about another 6 hours of activities I'd like to share with you tonight. I don't think we're going to get there, but we'll see what we can do. All right, what are we seeing? What are we seeing? I don't know. I think this tank they've melted more than in this one.
Excuse me, sir.
Yeah.
Some impurities are added, so it decreases the melting point, so that in the salt water, so ice will take more time to dissolve with in ordinary water, so ice will dissolve more.
So in Canada, when there's snow on the roads, they sprinkle ice on the roads. And they do it to make sure that the ice melts and gets off the road. That's not necessarily the same as what we're doing here, but that's what they do in places like Canada. We will come back and talk about your idea about the melting points. We'll come back and we'll talk about that tomorrow. So I'll just spread that out so they're more similar. So I think these ones are kind of at least half or a third gone. Left, sorry, I think these have lost very little. Maybe a third has gone. So I think this one is melting much faster. So we've had some people think some is fresh is fast. Some are thinking salt is fast. We've got some people going salt lowers the melting point, the freezing point. And we've got Canadians that sprinkle salt on their roads to get rid of the snow. So one of these ice cubes is just about completely gone. So which do we think is which? So this one's melting faster. This one's melting much slower.
Yes, sir.
Which tank is which? Tank A, tank B. Who thinks salt is tank A?
Sir, I think the salt is tank A.
I think that tank B is the
Added salt water in tank A and normal fresh water in tank B.
Yeah.
Yes.
I think
so far we've been looking at what's been happening with the ice. I'm just going to put a couple of drops of food coloring. I'm just going to try and drop it on the ice that's left there, and that'll show us what's happening with the water around the ice. So I'll put a drop on that ice cube and a drop on top of there.
Okay.
There
Sir, B is the fastest.
there seems to be a big difference between what's happening in those tanks.
Yes, sir. The A is not they're not getting a
One with the
dissolve.
salt water
The B
has
is
not
getting
even
a
started
dissolve
dissolving.
food color.
So this is one of the ways we can give ourselves more observations to help us think about what's happening. Before I put the food coloring in there, you were just focused on the ice. When I added the food coloring, now you're also seeing what's happening in the system.
Density of the salt water is more higher than the density of the fresh water.
That's certainly true.
Food coloring
certainly
in
true.
tank number A is almost not moving at all.
Yeah.
Yes, sir, it's not moving the food color of A.
It's like floating on the
As if it's
moving,
gone to
it's
sleep.
dissolving.
but B is actually dissolving.
Yes, sir.
But certainly it's mixing.
Dissolving
It's
the
mixing.
Sir, its density of salt water is more than fresh water.
So why does that explain what we're seeing? It's true, salt water is denser than fresh water, but why does that explain what we're seeing? We're seeing very different mixing of the water here, almost no mixing of the water here. Why are we seeing this mixing? What's happening here?
The amount of impurities is less.
The amount of
What's going on?
I think in tank A, the salt had occupied some of the free space, so kind of slower.
It's a salty water, na? So B is the fresh water. There is not a like a vapors means.
So why are we getting mixing here? Why is that mixing so much?
There are less impurities as compared to.
There is not a molecule.
That's why.
So it is totally pure and free space.
Well, there's still 99% water here. There's plenty of space for it to move around. It is denser.
Sir,
yeah.
Sir, maybe in the tank B, the temperature will be higher.
Sorry, say again.
Maybe in the tank B, the temperature will be higher.
No, temperatures were the same. The water in both tanks was sitting in the same room for days. So the water in those tanks, exactly the same temperature. And I put about the same amount of ice in each, as close to the same as I could. Yet in one, we were getting a lot of mixing, and the ice is all melted. Here, we're getting no mixing that we can see, as indicated by the food coloring, and the ice is still there. It's,
Yes,
2/3 of it is still there.
Fresh water is the getting faster, sir.
Canadians were wrong.
Canadians are wrong. I have some Canadian friends. I'll let them know that they're doing the wrong thing, and maybe they are. Maybe they are, or maybe
the whole nation, such a big nation,
is wrong. Yeah, or maybe they're doing it and something else is happening. That wouldn't be the first time. I tend to like Canadians, like Indians. They're nice people. They're nice people. Let's come back to this. The thing which is really common, the thing which is common between both of these is not things dissolving faster. When you say dissolving, I say we're seeing mixing happening. So it's not really dissolving, we're seeing mixing. If you go online to Google, and Google has got lots of wrong answers out there. If you go into Google and... Sorry, I don't understand. my Google is telling me it doesn't understand. That is so funny. If you go online and search for this activity, you will see it. And in many places, they will tell you that this demonstrates diffusion. Now, diffusion is a process that gets driven by the motion of particles. And the hotter the system is, the faster they move, the faster diffusion happens. That's absolutely true. What I've just said, that's absolutely true. But it's got just about nothing to do with what we see here or here. This is all about a process of convection. So in the hot tank, this is 80 degrees, or it was. It's in a room at about 20 degrees. And so the water in this is cooling, and it cools from the edge, cools from the surface. Just like we were discussing at the beginning of the session, surfaces are really important. So this cools from the surface, so the water next to the glass gets cold, cooler, not cold, but cooler. And cool water is dense, and so it falls down. So that means that warm water keeps being pumped around, setting up a convection current. And because this was so much hotter than the room, it was cooling a lot, and so it was convecting a lot, not diffusion. So it's an actual flow of liquid. This at room temperature was just ticking over. There's a little bit of heat change. Perhaps it was picking up heat from here. Here with the cold water, it was only gradually picking up a little bit of heat from the room, but it wasn't convecting. So it wasn't changing temperature quickly, and so it wasn't starting to convect. So water, when it gets hot, becomes less dense and it rises. Water, when it cools, becomes more dense and it falls. And that effect of density and convection is what we were looking at in these tanks. Salt has an effect on ice, but this is really all about the density. Here the salt water is very dense. The cold water, as it melts from the ice, even though it's dense, fresh water, it's not denser than the salt water, and so it can't move. It can't fall through the salt water. So we get cool water collecting, ice cold water collecting around the ice. So this ice is surrounded by icy cold water. Over here, the ice cools the water around it. The water around it heats the ice. The cool water falls away, allowing warm water to come up. And so the warm water comes up, melts more ice and cools down and goes down, bringing more warm water with it. So all of the heat in this tank was able to move past the ice and melt it. Here, even though it's the same temperature, most of the heat down here isn't circulating around, bringing the heat to the ice. And so all of these are really about convection and how it can be driven.
So does the salt prevent the water particles from moving around?
No, so it's not viscosity. It's just density. It's just density. So it's nothing more than that. It's just because it's very dense. The same thing can happen. The same thing can happen in lakes in cold mountainous areas, where once the water in the bottom of the lake gets very cold, the lake stops convecting, stops turning the water over. In a normal lake, you get quite a bit of the water moving from top to bottom around the lake, warming up in the sun, cooling at night, falling down, cold water coming up, getting warm the next day. So in many lakes, in sort of southern India, for example, the lakes will normally be turning over. In alpine lakes, the bottom water can sometimes get so cold it won't turn over. But as global warming is coming along, all of these systems are being interrupted. So one of the big problems, one of the big challenges, one of the big worries we have as the global systems are warming up.
So,
We've got more set. We've got more.
What
We've got more.
stops the salt water from turning around?
Just the density gradients. So in that tank, you're talking about in tank A?
Yes, sir.
So it is denser than the coldest of the ice water. So the ice melts, it makes cold water, cold fresh water. But even though cold fresh water is dense, it's not denser than the salt water. And so it will float on the top of the denser salt water. In the other tank, as the water around the ice gets cold, it gets dense and it falls all the way to the bottom of the tank. And that means the other warm water can come up to where that water was. And so the water starts convecting, starts turning over. In the saltwater tank, in the saltwater tank, it falls, but it's not dense enough to fall through the salt water. So it stays at the top and you get a cold blanket. In some parts of the world, as things are heating up, these alpine lakes are suddenly warming up so much they are turning over for the first time in thousands of years. And that's destroying their ecosystems. But one of the things which this kind of shows you, I guess, a little bit is how water, as it changes temperature and salinity, can lead water to move in big currents. And one of the largest on the planet moves water from the pole to the equator. So the water at the equator gets warmed, it moves to the surface. That pulls cold water in underneath it, and that pulls colder water down from the Arctic. And as that comes down, the warm water then at the equator gets pushed back towards the poles. And so this sets up a big circulation system. It's called a thermohaline conveyor that serves to take heat from the equator up to the poles where it gets cooled. Now, one of the things which is happening with global warming, changes of sea temperatures, is a lot of these convection systems are starting to change. And as they change, we get changes in monsoon patterns, we get changes in rainfall, we get changes in where there is ice. So North Pole is down to about 1/3 of what it used to be. And so if the pole isn't there, which might be in the next decade, we may lose the North Pole, then if that's not cooling the water, then the hot water may stay in the tropics. And that will mean more cyclones, hurricanes, and typhoons. And so tonight we've just been looking at what happens in a little glass jar. And we've just been looking at some fairly simple bits of science, but this science is what is underneath the biggest systems on our planet that are affecting our weather and our health and the future. And you can see lots of them are kind of driven by heat. And with global warming, all of these heat engines are changing how they work. A lot of them are speeding up. Any more questions about that? We're a little over time at the moment. So we've taken a bit of a journey. I think, let me just check with my good friends at the Science Centre to see whether or not we've got another 7 minutes to go and do one final activity. Could I be allowed that 7 more minutes for one more activity?
Yes.
Fantastic. All right. I'll try and make it a good one then. All right. Let me just change cameras and hopefully do an activity that will put a smile on your face. Let me just clear some space. So surface area is important. Densities are important. They really do affect how the world works. Now, here's an activity that you might like to try. Here is just one of my plates. I'm very generous. I have to eat with my fingers because all of my plates are in my study doing science. But I do have here a nice collection of M&Ms. So these are a lolly which has got sort of brightly coloured shell, brightly coloured sort of candy shell, and lots of colour in the chocolates.
US version of gems.
Yes,
So
sir,
you
I
can
know
you're familiar with M&Ms? Good.
Yes, sir.
Can you get? I think you can
I've
get
tried them out.
Excellent. Excellent. Just in the name of science, I'm sure you weren't just eating junk food. It was all a scientific experiment. And what I'll be able to give you now is a reason to go and buy M&Ms and tell your teachers that it's just for science and they should be buying them for you. You can try that. See if they like that as an idea. And so I'm just putting some colors at random around here. And I'm not putting the brown ones down because I prefer to eat the brown ones. And just about done. All right, so made a nice little ring of M&Ms. Can I get one more in? There is a mathematics problem here. And now, see, in my study, even the M&Ms are in chemical jars on there. So in case the tax man comes around, I can actually see that the lollies I'm buying are actually for science. It is a business expense. And now, what I'm just going to do as quickly as I can is I'm just going to pour some plain water across the plate, just so that it comes up about halfway on the M&Ms. So I don't want them swimming. It'll be about halfway up. And I know my table is at a slight tilt. So I'm going to just I'd like it to be nice and level. So I'm just going to put a little bit of paper under one end and make it just a little bit more level. And here we go. 3, 2, 1. Should do this quickly and then stop. And now we'll see what happens. This will take the remaining 5 minutes. So we've all kind of handled colored candy, and it's kind of come off in our hands.
We can
What
see
else?
the colors coming out.
Wow.
Yeah.
Amazing.
Amazing, sir.
What else do we notice? There's so much to notice about this.
So there's a ring being formed.
Yeah, it's all kind of coming out. It's kind of like a rainbow. They're not really mixing.
It's like a rainbow, sir.
They're not really mixing.
Scattering.
Why aren't they mixing?
That's a great question. That's my favorite question from the night. Why aren't they mixing? Why aren't they mixing? Where are they going?
Yes, sir. I have a doubt of this.
That's kind of pretty amazing. If the table was more level, we would see just the bands just going all the way out. While that's happening, I'll try not to disturb it too much. So why are we getting that pattern? You had some great questions. Why aren't they mixing? Why aren't they mixing? Why are they
think
kind of
we need
running?
to give them some time to mix.
Yeah, if we wait long enough, maybe they will mix. Just trying to get some other colors over here. And yellow.
They will form black color.
Sir, it's form a black color, sir.
We're getting the colors are starting to mix now, but when they sort of first came out, they're all pretty much kind of running out all together. I'm going to just gently move that over to the side. It's pretty hard to move it without disturbing it. And we're going to see something even stranger than that tomorrow. So bring your friends. What do you expect to see when I do the same with this pattern? What do you think?
I think black color.
It's a black color, sir, I think.
And this will be our last activity for tonight, because we shouldn't hold you back forever. You will see on the other plate, they are gradually mixing. So tomorrow, I want you to try and tell me, why does the color run out the way it does? Is it diffusion? Some people were saying osmosis. Lots of different ideas. What makes the colors run out? Why do they spread out? I think that doesn't surprise me. It doesn't surprise me that the color spreads out. If you drop ink on a page, it spreads out. That looks normal. That looks unsurprising. But here, the colors, they sort of came to each other and then stopped. If you just wait a few minutes, we'll see what happens when these colors meet.
Sir, why these colors are not mixing?
Well, they're still spreading out. They're still spreading out. They haven't quite reached each other yet.
Sir, I didn't notice the red spreading out.
There is a difference. There is a difference, isn't there? Yeah, the red is not spreading out as quickly as the yellow. Yeah. The yellow is the quickest at spreading. The red is the slowest, and the blue and the green are somewhere in between. That's another good observation. Maybe it's because the water isn't as high up here, or this is deeper. Maybe. But if we want to check that, we need to go and do a good controlled experiment.
So these colors are now mixing.
They're kind of at the point where they're just kind of reaching each other now. So if we mix the yellow and the blue,
like
we
cells with nucleus.
We'll just give this another minute or so. If anyone is really busy and they need to leave, of course you can go. But we're live streaming this on Facebook, watching grass grow slowly. That's kind of what it feels like. It's a spectator sport, dissolving candy. But I don't know if you see it, but I see something kind of a little surprising.
The yellow is kind of moving away, and the blue.
The yellow is moving towards green.
Yeah, they're coming around the bottom.
Yellow.
Yes, sir. The green and yellow moving up away from the blue.
Yeah, but what do you notice about this edge? The blue was coming out in a nice big round edge, and so was the green. But where they came together, are they mixing or are they stopping?
Stopping.
They're pretty much stopped.
Yes, sir.
They're pretty much stopped. Over here with the yellow and the blue, we're not getting green. Those aren't mixing. They've kind of come up to each other and stopped. Maybe the same is happening up here with the red.
Yeah.
Kind of, I think maybe it
Red is very slow.
It's happening slowly, but where they're coming together, we're making these kind of edges. They're not mixing. They're not mixing. And that looks really different. That looks slightly puzzling. So
that's bizarre.
I think it's bizarre. I love that word. It's bizarre. That's enough to make me think and maybe make me go and try it and to work out what's going on. All right, my friends, it's well past the 60
kind of
the 60
it's
minutes.
starting to mix at some points.
It is a little, yeah. There's a bit of mixing
Yeah.
happening here now. Maybe over
It
here.
is mixing very little
Yeah.
in green and yellow variable.
Eventually, but yeah, a little. Not much mixing happening up here yet.
Okay.
So have a think about what's going on there. And those of you which are joining me tomorrow night, maybe we can share some ideas about either what you've tried and discovered, or what other ideas you've come up with.
Is wrong that way.
Yeah. So tomorrow we'll be trying and failing again to get through 20 great activities. So we're going to do as many as we can. But we're going to spend some more time working through how you think about things. So it's going to be very fun. It's going to be very confusing. But in the end, hopefully you'll be very curious and you'll spend a lot of time afterwards rethinking some things that you thought you already knew. So a few of you have been asking if you can contact me. You can get in touch with me at the email address I'm just putting in. It's just thesciencenomad, one word, at gmail.com.
Is it the Science Nomad or overseas?
Yeah, the is part of it. So the Science Nomad within quotes. And certainly if you wanted to, I'm just going to pull up a link to Facebook, which I'm happy to share with you as well on there. Are there any quick questions before we finish for this evening? Sorry, I couldn't catch the audio. If you'd like, you can just type that into the chat window. So I'll give you some time to do that. In the meantime, again, I would very much like to thank my great friends at the Regional Science Centre there for bringing us all together so that we can share, ask questions of each other, and hopefully work out how we can learn better together. I've had a great time tonight. The room is full of a dozen other chemical experiments and 2 days worth of computational thinking. So I will talk to my friends at the Science Centre to see about when we can come back and spend some even more time with all of you wonderful enthusiastic learners. So I've had a great time tonight. My friends at the Science Centre, thank you so much for bringing us all together. I will go and tidy things up and get ready for tomorrow's evening's event as well. I hope you've found that inspiring in some way to keep thinking. Thank you.
Yes, dear students, teachers, and Dr. Stuart from Australia. Now it is time for all of us to say a big thank you to Dr. Stuart, to our viewers, participants, students, teachers, and all well-wishers. Hope you have enjoyed the topic, but keep on thinking. And if you think, he will be happy. He is not there to answer you. He is there to make you think. This is his approach in the field of science communication. So please do not be in a haste to answer these questions so early. Continue thinking, try thinking, till a final solution reaches you. This is the advice of Dr. Stuart to all of us. Thank you all. Hope again we meet tomorrow, same time.
Thank you, sir.
And the link will be given to all of you tomorrow morning. Thank you, sir.
Thank you. All the best. Stay safe.